Okay, today we're going to be looking at Chapter 11, which deals with solutions in colloids, and we're going to get started. Now, what I have ready, I have it on my desk, but have a periodic table handy if you need it, and I do have a graphing calculator ready to go. And that's the only thing I'm going to be able to use through all this here. So, let's get started. All right. Chapter 11 deals with solutions, first of all. We'll do colloids near the end, but solutions in general, something simple to see. They're giving us an example of some potassium dichromate at first, which is a nice orangish powder. Dissolves quite easily. Put it in a little flask like that, stir it around. It's going to have a solution that's got that orange color. It's a homogeneous mixture. In the past, we actually would call this aqueous solution. And we would point out that the solute was the potassium and the dichromate, and the solvent is the water. Now, in the past, we actually said the solvent was always the water, but we are going to see these vary some. Solute and solvent are going to be different things making up these solutions. All right, so we're going to first do some definitions here. The first definition we're looking at is spontaneity, or spontaneous reactions. Now, we're showing this nice little demonstration to explain what's going on here. So what we have is we have two sealed containers. One side is pure helium and the other side is pure argon. If we open up that valve in the middle, and this is just you turn it sideways and it opens, we would expect those gases to end up mixing evenly eventually. Might have one side moving faster than the other at first, but eventually it'd be about a 50-50 on both sides. And there's nothing we can do to stop that, and there's actually nothing we can do to undo it by just flipping this valve. So if we actually go back to closing the valve, it won't somehow separate the helium and argon. Once they've mixed, they're going to stay mixed. Well, that's a spontaneous reaction. There's nothing we can do to control that, and there are plenty of other spontaneous reactions or spontaneous situations. Dissolving of sodium chloride in water is a spontaneous reaction. Put the solid sodium chloride into like a beaker. As long as it's enough water to totally dissolve, it will eventually dissolve it, and there's nothing we need to necessarily do. When we do that, where we stir it, that is just to speed up the process. But if we were to actually go back to this, just put that potassium dichromate in that water, given enough time, it would eventually dissolve and you'd get that same thing. Typically, we stir it just to speed the process up. Okay, so spontaneous process is just something, where there is a favorable decrease in the internal energy, or a favorable increase in the disorder. If actually both of these are true, it's guaranteed to be spontaneous. But if at least one of those two is true, there's a chance it's spontaneous. Now, the exothermic is typically a huge factor. Almost all of the common exothermic reactions are spontaneous. But there are exceptions. But that doesn't mean that only exothermic reactions, because we're going to see there are endothermic reactions that are spontaneous as well. So we're going to expand on these two by looking at an exact example, which is the solvation. Now, solvation is just simply as you take a solid something and you put it in with some water and you make it an aqueous something in that water. All right, and what we're showing here is the process that's involved. So, and rather than say this is water, I'm going to change this to say it's the solvent. So it doesn't matter if it's water. So our solid substance, we're going to call our solute, the very first process that's going to have to happen for it to dissolve and become aqueous is we're going to need to separate the actual solute particles from each other. That's what they're showing here. It's going to overcome those intermolecular forces. So those intermolecular forces get broken, and now these are individual species floating around. So that's going to require some energy. Over here on solvent, I used water as an example, but it could be anything. Same type of thing. We're going to have to put energy in to overcome the intermolecular forces of the solvent-solvent interactions. So putting some energy into it. All right, The expanded solvent and the expanded solute will then mix with each other. that mixing is definitely going to give us back some energy. And that's simply because we're overcoming that isolation. As long as it's a compatible intermolecular force, that's definitely going to be an advantage. All right, so we have two steps that are definitely positive, one step that's definitely negative. What's the value of the overall process? Well, it kind of depends on the species and what's going on. Sodium hydroxide, for instance, when it actually dissolves in water, the solute and solvent do get separated. But when they mix, there's actual an overall addition of energy. Mixing actually is a lot more energetic. So this particular reaction has an exothermic delta H. It actually gives off a tremendous amount of heat. Matter of fact, it's actually kind of a problem when we make it for like a chemistry lab. If we want the final solution to be room temperature, we have to make it in plenty of advanced time so it has time to cool back down, because it will get noticeably hot. It's not so hot that you could like burn yourself per se, but the glass container that you're mixing in will get hot to the touch. Alright, so we have an exothermic reaction that happens with solvation. We also have the possibility of endothermic. So I have ammonium nitrate here. Same type of process. We're just dissolving that solid in water. We have the positive energy from the solvent and the solute separating, but when they come back together, we don't get nearly as much energy back. This particular reaction is endothermic. So have a delta H that's actually positive. It absorbs heat. So the surroundings, like the glass, or you, if you were to touch the glass, are going to give off heat, give it back heat. You're going to feel it getting cold. This is instant cold pack. So if you ever seen those where the first aid kits have little baggies in them, they're rupturing the internal bag, which has just water in it, and the powder floating around it is sodium or ammonium nitrate, and it gets really cold very fast. All right, so this solvation process, the heat of solvation, can be positive, can be negative. As long as it dissolves, solute and solvent, as long as they mix and they mix and make a homogeneous mixture, you're going to have a positive or a negative delta H. Sometimes you can't tell because it's such a small value, it doesn't actually translate to a large temperature change, but there's hardly ever an expectation where they're going to be nearly zero. With the exception of type of reaction we're going to see later on, miscible, where they mix in any ratio. All right, some more terms. Electrolytes. Electrolytes are just ions that float around in a solution. Now, when we talked about these in Chem 1, that solution was always water. It doesn't necessarily need to be water per se. The necessary component is the ions are stable in whatever solvent you're dealing with. Now, this is a sample that's dealing with water, and we just have some KCl, something we know is very soluble. Because it's very soluble, it wouldn't take much potassium chloride at all to get a lot of electrolytes transferring through there, and therefore a huge amount of current could transfer. Acetic acid, vinegar, doesn't nearly separate as much. It's not going to create as many ions. It is enough to actually create a current, so that light bulb would come on a little bit. And ethanol over here on the left, we wouldn't expect it to do much of anything. If we make the solution extremely, that won't make a difference. Never mind. Now, there's not much we can do to make that conduct electricity. All right. The ionic electrolytes are forming those electrolytes simply because it dissolves. As long as you have an ionic compound that dissolves, you're going to have electrolytes. Now, not all ionic compounds dissolve. We got chlorine here. If we think back to our solubility rules, AgCl mostly stays a solid in water. So it's not going to create any electrolytes per se. So you need something that's quite soluble, and as long as it's soluble, the ions will get surrounded by the water. Matter of fact, we can actually guarantee that all negative species, the water is going to arrange themselves where the hydrogen is closest to the negative ion, and the cations, the oxygen gets arranged closest. And that has everything to do with the polarity of the water. So we bank back to our Lewis structures and we started talking about dipole moments and electronegativity. We said the electrons were moving towards the oxygen. That negative charge that builds up on the oxygen is what gets attracted to the cations, and the positive charge that's near either one of the hydrogens is what gets attracted to the chlorine. Okay, this also happens on covalent bonds, so it doesn't have to be ions that form electrolytes. So what we have here is something we know is going to form a charged species. HCl is one of our strong acids. If I add that to water, the H gets donated totally to the water, making H3O plus, and the chlorine floats around. Well, ions are all it takes to be considered electrolytes. This is going to be a strong electrolyte just because it's the nature of an acid. All right, some terminology that we've actually talked about prior to this. We're just going to expand on it. Solubility can be measured as just saturated or unsaturated or supersaturated. And there's plenty of room between these two where we're not quite saturated or unsaturated. We typically reported that in concentrations before, so we would see that there is 1 molar HCl, there is actually 6 molar HCl, and saturated is 12.1 molar, at least at room temperature. But anything under that is just simply, in this category, undersaturated or unsaturated. Supersaturated is not something we can do too easily with HCl. There are plenty of things that we can supersaturate, and we take advantage of some cool properties with those. Something you might come in contact with on a relatively daily basis, possibly corn syrup. Corn syrup turns out it's just a supersaturated solution of sugar water. It just happens to the sugars are actually coming from corn. All right, gases can also be dissolved in water. Now we are talking about solutions, but technically this is still a solution. The gas is just the solute. We typically see that all gases, the solubility decreases with temperature. So hot water holds less oxygen than cold water. And all gases actually do that. So there's no real exceptions to this. They all drop. Now, we actually can predict that. Henry's law is used to actually calculate the solubility based on the partial pressure of the gas using Henry's law gas constant. Now, this one's not as complete as you get in later chemistry classes because this one doesn't take in consideration that Henry's constant for a particular gas will be limited to the temperature you're talking about. Because just like this curve shows, at a different temperature, the maximum solubility will vary quite a bit. Henry's law, as this equation shows, doesn't actually talk about the temperature. So if we see it, we're going to be ignoring the effect with temperature. Just know that it does change with temperature, and Henry's law needs to be fixed for that. But that's past Chem 2. All right, so here's how we could actually use this. Alright, so at 20 degrees Celsius, a concentration of dissolved oxygen in water, or the concentration of dissolved oxygen in water, has a partial pressure, or at a partial pressure of 101.3 kilopascals, is 1.38 times 10 to the negative third moles per liter, molarity. Use Henry's law to determine the solubility of oxygen when its partial pressure is 20.7. The approximate pressure of oxygen in the atmosphere. Okay, so, alright, we are going to use Henry's law on that first set of data to get the K for oxygen. So our concentration is 1.38 times 10 to the negative third. I'm going to change that to molarity. We're going to solve for K. And then our pressure, it's talking about 101.3 kilopascals. Now, units of K do vary, but it's fine to have them in moles, molarity, and kilopascals. So all I'm going to do for this is take that 1.38 times 10 to the negative third and divide it by 101.3. And I'm just going to say my K is 1.36 times 10 to the negative fifth. And my units for K would be molarity per kilopascal. Alright, now we are going to use that K with this pressure to determine a new concentration. So the concentration that it's wanting to know here, the solubility, we're going to take that K we just solved for, and we will multiply it by the new pressure of 20.7 kilopascals. And this will work because the kilopascals cancel out, and I don't need to do anything on my calculator except say times 20.7, the new pressure. And I get that that concentration is 2.82 times 10 to the negative fifth. I said negative fifth, that was negative fourth, wasn't it? Negative fourth. Now keep in mind, if it changes temperature at all, Henry's law as we see it here won't work. So this is a very limited use of Henry's law, at least for us. Other gases do this. Ammonia actually dissolves in water quite easily because it reacts. So the Henry's law for ammonia varies based on what other things are in the water and what the pH of the actual water is. So Henry's law doesn't work quite right for us. And that's simply because the ammonia bumps into water quite easily, transfers an H gets transferred onto that, making NH4 positive and OH negative. As long as there's the ability to do that, the solubility of the NH3 is higher because some of the NH3 gets turned into NH4 plus. Same thing kind of happens in our oceans with CO2. So CO2 bumps into water and actually makes H2CO3, carbonic acid. Now it doesn't make a lot of it. The reaction going forward isn't very fast compared to how fast it is going backwards. So there is some carbonates build up in the ocean and some effect of that is acidifying the oceans. And we are actually seeing that on a global scale, that the pH of the ocean is actually slowly getting more acidic. Not by a huge margin, but it's enough that's actually something to be concerned, because we have no idea what it's going to do. All right, when the CO2 is allowed to build up, and there are a few natural places that happens, we see another failing of Henry's law. So Henry's law tells us how soluble CO2 is in a lake, for instance. But what it doesn't actually keep in mind is that if we have a deep lake, it turns out that Lake Neos is a very deep lake. Some of the water near the bottom is much, much, much colder, therefore it had a lot more CO2 in there. Well, back in 1986, there was something that happened in that lake. Maybe an underground landslide, maybe just an excess amount of rain on one side. But something caused some of that cold water from the bottom to come up towards the upper part of the lake a little bit too fast. Suddenly that CO2 is less soluble in it, and it actually came out very rapidly. I got a slightly better video here. Or not a video, but a better picture here. Now this picture was taken shortly after the incident, and you can see like the discolorization, and it looks like something hit this. Kind of was a big wave, but it was a much carbon dioxide in the wave as water. So a huge amount of CO2 came out of the lake very, very rapidly. And because CO2 is a little bit more dense than air, it hugged the ground. It was enough that it knocked over trees, and it went down in a valley, and which is why our slide says on here in your book talks about 1,700 people die, something like 3,000 cows. So it didn't hit a huge population area, but it was big enough that it actually caused a tremendous catastrophe. Now, at least in theory, it could happen again. But what they've done, engineers that is, to figure out actually to make this safer, see that little fountain there? Well, it's not really pumping anything. what they basically did is they run a pipe deep down into the water, and they just initially pull some water up in there. So actually they did have a pump to start the process. But as the water comes up and the CO2 comes out because the water starts to warm up, that CO2, being a heck of a lot less dense than air, is definitely going to come up the tube. But it's actually going to help create suction, because now the water is a little bit less dense because there's less stuff in it. The water itself comes up. So once they started the process, this is just ongoing. And that will go on and on and on until the CO2 level in the lake is low. It's been going since the 90s. No reason to expect it's going to stop. There is another potential disaster on this lake. I'm pretty sure it's in this picture, that little natural levee there. So this is a crater from like a ancient volcano, I think it is. Well, the levee on the backside is just a natural barrier. Well, the water has been seeping into it over the millennia and it's weakened it up. There is a chance it will fail. Regardless of how much fails, it will probably cause another outgassing effect. Now, there's 2 lakes in the near Cameroon that have a similar issue, and there's one that's actually got more methane in with the CO2 as well. And there, instead of actually just letting the water pump up, they actually put a little platform out there, and they're separating the methane out of that CO2, and it's powering, I think it's 24 megawatt power generation. So pretty cool that they're just playing around with the solubility of water. But it's kind of neat that they're mining a lake for methane. All right, miscible was a term I just mentioned a few slides ago. I actually said that that's going to happen when that delta H for solvation is approximately 0. Now, reason that's important, turns out with very exothermic reactions or very endothermic reactions, the heat can stop the mixture. But if it's about 0, that actually leads us to this situation where, a solution made from a solute and a solvent could be miscible. They'll mix in any ratios. Now, they're showing antifreeze. It's one that can. Turns out ethanol can actually mix in almost any ratios as well. And that really just does mean it could be 90% water or 90% ethanol, and it's going to mix. It doesn't matter what that breakdown of the ratio is. Now, on the far other extreme is immiscible, where they absolutely do not mix. Oil and vinegar do not mix. There's nothing we can do to stop that. There's plenty in between here. So this is ethylene glycol. If I were to go with butanol, which is 4 carbons, and on the end is an OH, it's an alcohol just like ethanol, but while ethanol can actually mix it in a ratio, butanol, only about 1 or 2% can actually dissolve in water. They're close in density, so it won't actually look like this. It'll actually look like water throughout, but if you were to shake the container, you could see the little turbulence in there where the 2 layers are clearly not mixed. Alright. Along with gases dissolved in water, we have plenty of solids that we can dissolve in water. We will also find the similar type of thing, that temperature will affect the solubility. This is not a good trend, though, in the sense that it's not always predictable. Some things get more soluble with temperature. Some things like sulfates, or many of the sulfates, actually lose solubility with temperature. And less predictable in how to shape the curve. Some of these are huge effects. So look at sugar. As you heat it up, it really changes its solubility. But things like salt, like the ocean, sodium chloride, it barely changes with temperature. It's almost flat. But they all change, and that's all we wanted to actually say here. So the solubility of solids mostly change with temperature. We take advantage of some of these with their solubility changing with temperature to actually take advantage of some cool little features. All right, so in that solution is sodium acetate. And it is a supersaturated solution. Now, that little disc there in the middle, as you flick it, that kind of reminds the sodium acetate that it can be a crystal. So crystallization starts. Now, the crystallization will start, and that entire container will get filled up with solid sodium acetate. And you notice this says reusable heating pad. That is simply because when this is all done, it just puts out a bunch of heat. These are nice little hand warmers, so if we're ever up north and you have to go out and shovel snow, you might put these in your gloves. Here in Florida, you might be lucky to have gloves. Not really a need for them for most of the time. But the nice thing about this particular heating pad is it's fully reusable, because that solid sodium acetate, to get it to redissolve, I just need to warm it back up, because the solubility will increase with water. Even though this will look like it's a total solid when it's all done, as soon as I start warming it back up, it's going to actually just go back into that solution. So put that into some hot water on a stove. It'll go back to looking something like this. You pull it out and let it cool back down, and it's good to go again. As soon as you flip that little disc, it's actually going to form that solid. Now, if you look on the internet, you can find this, and there are actually people that will make a solution of this and then stick their hand down in it. The one video I've seen that it is legitimate, it's a little girl doing it, and if you actually do it right, it's going to work fine. But if you make the solution too concentrated, that process, reforming the solid, produces a lot of heat, and you actually can cause some burns. So if you ever considered trying it, good luck. I've decided I'm not going to do that one. Alright, all this stuff with our solution is going to lead us to some very interesting calculations. Now, these calculations aren't talking about the particular solute as how it does things. So we're just actually treating the solute as a general impurity. But solutes getting dissolved in there will change the properties of the solvent. And those properties that are changed are the colligative properties. So if we were to make, and we will just talk about a salt water solution, and not solid, we're going to dissolve it. So it is salt water. And we are going to say it's water, so the solvent is water. What we're saying here is the vapor pressure of the water will change, the boiling point of the water will change, the freezing point of the water will change, and the osmotic pressure of the water will change. And in many cases, it won't necessarily matter what the impurity is, it'll just matter what the concentration is, how much solute is in there, not what that solute is. Alright, now the amount does vary, and unfortunately for us now, the way we actually measure the amount, or the solute to solvent, so think about it this, we're going to actually want to get a relationship between the solute and the solvent. Well, how that relationship is looked at is kind of important for the colligative properties. What I mean by that, sometimes we want to look at moles of the solute. Sometimes we want to look at grams of the solute. Sometimes we're going to look at the volume of them. So there's different concentration terms we have to look at for the different colligative properties. So right now we're going to expand our concentration terms. Now prior to this class, in Chem 1 we covered molarity, because that's the general way we see things listed in a chem lab, because it relates moles to the volume. We also saw parts by mass, because that was mass percents. If you take the mass of a solute, mass of the solution, that's just going to give you your mass percent. Alright, those were the two we looked at, but what we didn't really look at was we didn't focus on the uniqueness of what the components were. When we talked about molarity in the past, we just said moles per liter. Well, now it's very critical for us to remember that it's moles of solute to liters of solution. So the solution is everything, because right below that I'm introducing this molality, which still has moles of solute on top, but the bottom is kilograms. but it's not for the solution, it's of just the solvent. Now, parts by mass is the mass of the solution, parts by volume is the volume of the solution, but molality, it's solvent only in the bottom. And mole fraction is moles of everything, technically. So moles of solute compared to moles of solute and solvent. So moles of everything on the bottom. All right, let's see how we do some of these. Let's actually figure out what our mole fraction is for this particular ethylene glycol solution. All right, so antifreeze. We want to get the mole fraction of ethylene glycol in a solution, give you the mass of it, compared to the mass of the water. All right, so it does say mole fraction of ethylene glycol, so I'm going to use this little Greek symbol, and I'm going to put the C2, and I'm going to cheat 8602. So I'm going to combine my two H's, my 4 H's and 2 H's. Alright, so that's my ethylene glycol, and the mole fraction on top, I want the moles of ethylene glycol. Let's see. Got to convert that to moles. So ethylene glycol, let's see, 12.01 times 2 for my 2 carbons. I have 6 hydrogens. Oops, how about plus? And I have 2 oxygens. So I get a molecular weight of ethylene glycol of 62.07 grams. That is going to be duplicated on the bottom, because on the bottom is going to have the moles of solute and the moles of solvent. So just rewriting that. But what I'm going to add to this is the moles of water. So 2.00 times 10 to the third grams, and 1 mole of water happens to weigh 18.016 grams. Alright, let's see what our mole fraction is. So 2.22 times 10 to the third divided by 62.07 is this. I'm going to divide that by that number again, plus 2.00 times 10 to the third divided by 18.016. Get a mole fraction of 0.244. Mole fractions will not have a unit per se. It's just going to be that. It's just going to, it's technically moles over moles, but we don't put units down for it. Now the mole fraction of this one could have been the mole fraction of water. Only thing we do differently is we'd have the 2 times the 18 on top. But that's how we would do the mole fraction. Alright, let's do the same components and the same amounts, but let's get the molality to see how we do this differently. Now if we were to back up and look at that slide where it talks about our concentration terms, we see that molality has on top moles of solute, on the bottom kilograms of solvent. Well, solute and solvent can be interchangeable now. So it says molality of ethylene glycol. It's defining the ethylene glycol as our solute. So on top of this, we're going to have something very similar to that previous page. So 10 to the third grams, and then we're going to convert that into moles of ethylene glycol. Was that 62.07 grams? I think it was. Yeah, 62.07. On the bottom, I just want kilograms of solvent. Solvent in this case is water. And I'm just going to put 2.00 kilograms. Because it was 2 times 10 to the third. Get rid of the 10 to the third, and I can change that to kilograms. A little bit easier on this one compared to that last one. So 2.22 times 10 to the third divided by 62.07 0.07, and then divide all that by 2, and we get a molality of 17.9. Alright, let's do another one. Alright, if you look at this, on this slide, I have the first one say calculate the molality of naphthalene in a solution containing 16.5 grams of naphthalene and 53.3 grams of benzene. And then right below that says calculate the molality of benzene with the same components. Reason I'm doing that, in the past, and most chemistry textbooks say the exact same thing. They say when you're dealing with a solution, the solute is always the one in a smaller amount. And in general, that's the case. If it's not actually ever defined one way or the other, the solute is the one that's in least amount. But molality in that calculation doesn't necessarily matter which one we have as the solute as the solvent. So we're going to define it by putting that of. So this saying molality of naphthalene, we're saying the naphthalene is the solute. So our first thing on this one is to turn that 16.5 grams of naphthalene into moles. And C10H8. C10, 12.01 times 10 plus 8 times 1.008. I get a molecular weight of 128.16. And on the bottom I will have kilograms of solvent, so just 0.0533 kilograms. So 16.5 divided by that value, and then divide all of that by 0.0533, we get that the molality is 2.42. Lowercase m should be italics, but my chicken scratch isn't going to show italics too well. Alright, the next one was the molality of benzene, given all the exact same stuff. Be nice if we could just do an inversion, but we really can't, because while we are inverting the equation, we actually want to look at the moles of just one of those species. So I am inverting those values, but I'm turning this into kilograms, and I will be multiplying this by the molecular weight of benzene. Six times 12.01 plus 6 times 1.008 is 78.11. Okay, calculator. 53.3 divided by 78.11 and then divided by 0.0165 gives me a molality of 41.4. Perfectly understandable for it to be that high, because this is mostly solute, because the solute is a huge amount compared to the solvent. 53 grams compared to 16 grams. But we're just doing this to show you that the solute and solvent are not are not defined by the amounts any longer. They're defined on how we ask the question. All right, next one, we're going to talk about concentration in parts by mass. Now, this particular parts by mass is silly to calculate it based on grams. And what we mean by that, let's actually take into consideration what this would be. Let's get the part by mass for the calcium ions in the water. So the mass of the calcium in that is just 0.25 grams. But the water was 100 liters. And we don't want liters because as a parts by mass, I need to convert that liters of water into a mass. So the very first thing I'm going to do is turn it into milliliters. And the reason I'm doing that is because I gave you the density of that water in grams per milliliter. Alright, look how big this number gets. Guess how small it gets. So 0.25 divided by 100 and 1,000 and 1.001. And I get parts by mass would be 2.5 times 10 to the 6th. And that'd be just parts by mass. And we could just do weight, or mass. Alright, but that's not what this problem asked for. It wants us to do this in parts per million. Alright, the only thing you need to do to turn a parts by mass number into parts per million is to multiply it by 1,000,000 times 1 times 10 to the 6th. And that is your ppm. So this 0.25 is actually 2.5 ppm. We could do something similar to that for the magnesium. We get 0.56 because math's going to work out the same here on what we do. Yeah, the number on the bottom, we're just moving the decimal because we're multiplying by a factor, or dividing by a factor of tens, really. But ppm, ppb, ppt, parts per thousand, are all just used to move that decimal part, so we have numbers that don't have those crazy big exponents. Alright, another way we could use these is to actually turn those percents, parts by volume, into conversion factors. So we have this wonderful bottle here of fine spirits. It must be, because it says so on the label, 11.5% alcohol. I don't know. I never like the stuff that lists the amount of alcohol. Let it age. Let it change naturally. Alright, but we want to figure out how much alcohol is actually in that 3/4 of a liter container. So 0.75 liters is the volume of the solution. This here, 11.5, does actually translate to, there's 11.5 milliliters of alcohol per 100 milliliters of solution. That's what 11.5 means, 11.5 over 100, right? Alright, but what I'm going to do here, I'm going to use that as a conversion factor. On the bottom I want the solution, and I don't want milliliters because this gave me liters. Now I could change this to 750 milliliters, but what I'm going to do instead is just say this was 100 liters of solution. And if I had 100 liters of solution, I would have had 11.5 liters of alcohol. The parts by volume, you just want the volume units to be the same. So use the ones you need to work with. Oh, this is just going to be simple as 0.75 times 11.5 divided by 100. And we get that that is, and it does want liters, so 0.863 liters, or 86 milliliters. Now, I'll put that in perspective. The average person, 100 milliliters of alcohol, so 0.1 liters, is right about that lethal amount, because that would be straight pure alcohol. So drinking that entire bottle there would be very, very dangerous. So keep that in mind, I guess. Alright. Unfortunately, molarity is the most commonly used unit in the chem lab. But that's not what we're going to need to do all those colligative property calculations later on. So we're going to need to actually have a working strategy of converting one concentration term to a different one. Now, some of these are easier to go. If I were talking about a mass percent, for instance, so 11.5% that ethanol, let's say it's 11.5% sodium chloride. Well, that does mean there's 11.5 grams of sodium chloride for every 100 grams of solution. And if that solution is just water and sodium chloride, we know this is 11.5 grams of NaCl, and then what would that be? 88.5 grams of water. 100 minus 11.5. So certain ones, because we can pull more out of mass percents, can be a little bit more helpful on turning them into other units. Alright, but we're actually just going to practice some of these so you can see what we're talking about. Alright, so one of these mass percents that pops up, one way we can do a mass percent calculation is with this problem right here. So hydrogen peroxide stored as a 30% solution. We want to figure out its molality. I did give you the density. Let's see if we need it. Alright, so molality, let's keep in mind our units of it, is technically moles over kilograms. More specifically, it's moles of what? Well, it says calculate its molality. It stands aqueous solution of H2O2. It's defining the H2O2 as the solute. So we're going to want moles of H2O2. And on the bottom, we want kilograms of water. Alright, so let's just turn that percent into something more useful and say that's 30 grams to 100 grams. Because that's what a percent means. And since we're doing that, that defines this as the solute. So that's 30 grams of hydrogen peroxide. On the bottom, it's not 100 grams of water, it's 100 grams of solution. Alright, well, getting this up here, the molality, I do want to just see that I'm going to take that 30 grams we just said was here, and we're going to turn that into moles. Let's see. 18.016 plus 16, another oxygen, 34.02. That would give us our moles of hydrogen peroxide. Alright, but I don't want solution on the bottom. On the bottom, I just want water. Can we figure out how much water there must be? Well, yeah. If this solution is just nothing but hydrogen peroxide and water, I can take 100 and subtract 30 from it and get 70 grams, or 0.0700 kilograms, the mass of water. So, I take my 30, divide it by that 34, and divide both of those by 0.07, and I get a molality of 12.6. Alright, another one of these. Same exact set of numbers, so it's still a mass percent, but now we want the mole fraction. Well, we already saw mole fraction. We know on the top is going to be the moles of just our solute. On the previous slide, we already just showed that the hydrogen peroxide was the solute. So we're just actually doing the exact thing on top here. Hydrogen peroxide, what was that mass? 3402. And since it's a mole fraction, on the bottom will be those exact same numbers because on the bottom is moles of everything. But now we also need the mole of the water in this case. So there's 70 grams of water. And mole fraction, which is the Greek chi, of hydrogen peroxide. Let's see what this gets us. Clear this out. 30 divided by 34.02, and on the bottom, in parentheses, we're going to have that number added to 70 divided by 18.016. Close those parentheses, equals, I get a mole fraction of 0.185. Again, no units, because it is a mole fraction. Oh, dropping my pen here. Alright, what else can we do with the percents? How about molarity, the common one we see in a chem lab? Still 30%. On the top, we're going to have the exact same thing because molarity wants moles on top. So that will look exactly the same. On the bottom, we want the solution, and we want the volume of the solution. Well, that's finally going to use that density. So we know that we had 100 grams of the solution. We're going to turn that into milliliters with the density. And we have to turn milliliters into liters. So 30 divided by 34.02 divided by 100 divided by, so times 1.11 and also times 1000. Molarity 9.79. Now you will see, especially your textbook, we have a lot of practice problems dealing with these mass percents and converting them into other units. Biggest reason we have that is, for the most part, that's easy to do because you just follow these steps that we just did. Just pick apart what you need out of that mass percent. Do you need the mass of the water? Do you need the mass of the solution? You just figure out what you need to get the units you want. Slightly harder if I go from any of the other ones to each other. So molality, for instance, into like mole fraction. All right, biggest confusing part here is the first thing we want to do is turn this into a fraction. So I'm going to say this, 3/1. And I'm not saying molality anymore. I want to define what it is. So it says it's molality of sodium chloride, so that must be 3 moles of sodium chloride. And since it is molality, that's saying 1 kilogram of water. Now we're not saying that's how much we actually have. We're saying that's the ratio that we must have. All right. Knowing those two components, that's how we're going to build a mole fraction. So mole fraction of the sodium chloride, what's going to be on top? The moles of the sodium chloride. And on the bottom is the moles of both. We need to convert that into moles. So I'm going to start by changing it into grams, and then I'm going to convert it to moles with the molecular weight of water. And let's see what we get. So 3 divided by, in parentheses, 3 plus 1000 divided by 18.016, close parentheses, equals. I get a mole fraction of 0.051. Not terribly hard when we follow the steps. Just turn your single value into 2. Anything over 1 works. And the mass percents, we put them over 100. But that's how we start. And then define what those would say the components are. Because not just 3/1, it's specifically 3 moles of solute over 1 kilogram of solvent. And then once you have a starting point, pull what you need to make what you want. All right, now on to our colligative properties. Now the 4 main colligative properties are right here. We have the first one, and actually how this slide is, I'd like to have that highlighted, because that's the actual equation we care about. The change in the vapor pressure is related to the mole fraction and the pressure, or the vapor pressure, of the pure solvent. Pressure always drops. So think about it this way. If I had a pool and I have a bunch of impurities, those impurities are going to keep the water in the pool and stop it from evaporating. So the vapor pressure drops. The water wants to stay a liquid longer. All right, right below that we have the equation for the boiling point increase and the freezing point decrease. So boiling point always goes up, freezing point always goes down, or we can again say the water wants to stay water longer. Boiling point goes up because it stays water longer. Freezing point goes down because it stays a water longer. Alright, but these both have constants. You have a Kb for the boiling point, you have a Kf for the freezing point, and then the M is the molality. And the last one, osmotic pressure. This is the Greek pi, it's just the capital pi. The osmotic pressure, or the pi, is the molarity times the R, the gas constant, the 0.082016. Excuse me. Oh. Paused that video because I had to sneeze, and I wrote that down wrong. 0.08206 liters, atmospheres, moles, and Kelvin. This is the only one that we do where the units are kind of important, because since you're using the R from the ideal gas law, you want to make sure your Kelvin is the temperature you use, and you're going to get the osmotic pressure in terms of atmospheres. Alright, let's apply some of these. So we just mentioned that vapor pressure drops. Let's actually calculate it. So I have a sample of glycerol, just 10 milliliters of it, added to 500 milliliters of water. The vapor pressure of pure water at 50 degrees Celsius is around 92.5, and we want to know what is the new vapor pressure. I gave you a bunch of densities too. Wonder what we need those for. Alright, so our equation is the delta P equals the X times the pure. Alright, now let's define things. The mole fractions of the impurity. So in this case, it's the glycerol. The pressure is of the solvent, so that is in this case the water. Alright, so I need to get the mole fraction of glycerol. I need the moles of glycerol. I gave you 10 milliliters. That's why we need the density, because we're going to turn the 10 milliliters of glycerol into grams using the density of glycerol, and then into moles using the molecular weight of glycerol. Would have been nice if I gave that on this slide. I have to calculate the here. Plus 3 times 16. I get a molecular weight of glycerol of 92.09. Alright, whatever that number is, it's going to go down here as well. But we're going to also need to get the moles of the water. We're going to do something similar. Density of water in this case, 988 grams per milliliter. And molecular weight of water, 18.016 grams. Whew. I could have made that more painful, huh? Alright, so just the mole fraction. 10 times 1.26 divided by 92.09 moles of glycerol. We're going to divide that by, in parentheses, that value, plus, in parentheses, 500 times 0.988 divided by 18.016, close two sets of parentheses, equals, look at that mole fraction. Mole fraction 0.0049. Alright, but I'm not even going to do anything with that. I'm not even going to write it down, because the only thing I want to do to get my delta P is multiply that by the vapor pressure of the pure water. So, times this by 92.5. I don't need to worry about the units. That value there is my delta P. So I'm going to write that over here. Delta P is 0.459. And it does say the vapor pressure lowering. But keep in mind, I might have just asked for the new pressure. The new pressure is 0.459 below the old pressure. So the vapor pressure of water at this with this impurity is going to be about 92.0 torrs. It barely changes. This isn't a huge effect, but it does lower it, and it will always lower it. All right. Next slide, we have a bunch of KB and KFs. Biggest reason I have these up here, I want to notice that there's not really any rhyme or reason. They're not related to molecular weights or anything. You can't even actually guarantee what the KF is if you have the KB. There's not like a multiplication factor. So you will be provided the KB and KF, or you'd be solving for them. And I also put the boiling points and melting points. And you can probably imagine I wouldn't ask you to have those memorized either. This entire table has items I will give you or have you calculate by giving you everything else. All right, let's actually see what happens here if I were to just put a small amount of ethylene glycol in water in our car. So cars, this should be about 50-50. So if you had 4 kilograms of water, you should have about 4 kilograms of ethylene glycol. But here we've just put 1 kilogram of ethylene glycol in 4 kilograms of water. We want to see how that affects the boiling point and the freezing point. Alright, both these equations look very similar. We're going to have a KB, over here we're going to have a KF, and both of them we need the molality. So right up here, we're going to figure out what the molality is. Now, it's the molality of the impurity. Since it wants to know the boiling point and the freezing point of the solution, we are talking about water being the boiling point and freezing point. Alright, so what is the boiling point? Or so, if we're figuring that out, we need to know the molality of the ethylene glycol. So I'm going to take my ethylene glycol, I'm going to rewrite that as grams, because molality, I want the moles up here. So ethylene glycol. 12.01 times 2 plus 6 times 1.008 plus 16 and 16. Gives me 62.07. Since it's molality, on the bottom will be kilograms of solvent. In this case, the water. 4.450 kilograms. I guess there's not a zero there, is there? Because without that decimal, that zero is not significant. Alright, now I am going to put this into my calculator. I'm not going to write down my number because I'm going to let the calculator do all the work later on anyway. So 1,000 times, oh not times, divided by 62.07 and then divided by 4.45. That value there is my molality, 3.62. Alright, to get my boiling point, I need the KB of water. It's not on this slide, it's on my previous slide. The KB of water is down here at the bottom, is 0.512. 0.512. 512? For some reason I was thinking that's supposed to be 515. And degrees Celsius per molality. KF is 1.86. Same exact units. This one we're going to multiply by the molality. This one we're going to multiply by the molality. So my delta TB is 0.512 times my molality. And we get the delta T is 1.85. I'm going to write that number down, and then I'm going to come over here and calculate this and write that number down. So over here for TF, 1.86 times the molality, and I get 6.73. Now these are both just delta T's. They're not actual temperatures per se. Alright, so our question is, what happens to the boiling point? boiling point always increases. So over here, the new boiling point of water, 101.85. That comes from the fact that water boils at 100. It's going to go up by 1.85 degrees. Well, where does water freeze? It freezes at 0, so our new freezing point is negative 6.73 degrees Celsius. And that is why we use antifreeze. That drops that below. Here in Florida, it's very unlikely we get anywhere close to that. Heck, Florida, it's kind of rare where we're at to even get hard freezes at all that last much longer than, a few hours. There are people that put just plain old water in their cars and do fine and don't have to worry about it freezing. I grew up in Ohio. I remember driving a car once and it froze up while we were driving. Probably didn't have the right stuff in there. Alright, so phase diagram is just showing what's going on here. Basically, the colligative properties affect how much water wants to stay water, or the solution stays solution. So we increase the water area. Boiling point and freezing point actually move in such a way to increase the liquid range. Osmotic pressure is just a membrane, thin little membrane, and water moves through it. Little 5th grade science fair project. Take an egg and with the right process you remove the shell without rupturing the membrane in there. So it's going to be an egg shape that's kind of like a gel type thing that bounces around. Well, you take that and you put that membrane, that egg, in very, very, very ultra pure water, like distilled water, and that membrane works like osmotic pressure, and the water molecules will move through the membrane much easier from the pure water side. So the egg will slowly get bigger and bigger and bigger. Now you can counterbalance that by taking a second egg, but in the second case you put it in a container with a lot of impure water. So just throw a bunch of salt in there. Suddenly the ions, or the impurity, stop the water from coming through, going into the egg. Most of the water comes out, and you'll actually get the exact opposite thing, where the egg will collapse on itself. But it's a spontaneous process. That semi-empirical membrane allows pure substances to move through much, much faster. All right, we take advantage of this on some very clever things. So hemoglobin, being a ridiculously huge molecule, getting its molecular weight is challenging because it's a huge amount. We can get it from osmotic pressure. Alright, so that's what we're going to do here. So here's my equation for osmotic pressure. Molarity times R times T. But if you notice here, in this problem right here, it says that the osmotic pressure is 3.61 torrs. I'm going to put that here. Now, something I already mentioned, when we're dealing with osmotic pressure, we need pressures in atmospheres. So the very first thing I'm going to do is just going to have and write down that I can convert that to atmospheres with this little relationship. 1 atmosphere is 760 torrs. Alright, we're going to actually solve for their molarity. Temperature needs to be in Kelvin, so I can't use the 5 degrees Celsius. I'm going to use 278.2 degrees Celsius. Or not degrees Celsius, kelvins. So I'm adding 273.2 to the 5. And now, let's solve for the molarity. Alright, so clear this out. 3.61 divided by 760 divided by R and divided by the temperature. Alright, it's going to be a very, very small number. 2.08 times 10 to the negative 4th. Now, I'm not going to actually use this number. I'm going to use what's in the calculator. I wrote this out because now I want to write out the units just to see what this is. Because molality is not the molecular mass. Molality is moles, in this case of hemoglobin, hemog per liter of solution. Somehow we're going to use this to get our molecular weight. How we're going to use that? Well, keep in mind, I'm going to work up here. Molecular weight is grams per mole. That's what molecular weight is. Should have that MW, just so there's no difference. Now, I did say this was made with 21.5 milligrams in 1.5 milliliters. Well, look at this. 21.5 milligrams is 0.0215 grams. And how about we write this in terms of liters? 0.00150 liters. I'm going to use this as a conversion. The liters would cancel. We'd have grams per mole. That's how we do this type of thing. Now, hemoglobin's a huge molecule, so we are expecting a very big number here. Even though there's a small molarity, there's not much in there. So take that, divide it by 0.0015, and also divide that by 2.08 times 10 to the negative 4. I just said I wasn't going to do that, and I just cleared out my calculator. Yeah. I only got 3 significant figures. 668,900 grams per mole. Interesting way of getting the molecular weight, but it's going to be darn accurate. There are better ways now, but that's actually a decent way to get it 10, 15 years ago. But now, the right type of instrumentation, you can get that far quicker with a lot more significant figures. All right. Our colligative properties, as we saw, work great on solutions of like sugar or amino acids, but not so well on ionic compounds. Reason that is, NaCl, we go back to thinking about our net ionic equations. NaCl is actually Na ions and Cl ions. These are both solutes. So if this is actually 1 molar stuff, this is like this is going to be like 1 molar, and this is going to be like 1 molar. So the actual effect down here on the molality should be 2. All right, the I there is the effective number of ions. Because here's the weird thing. Even though sodium chloride separates into 1 and 1, we don't get an I of 2 for sodium chloride. The reason we don't is because there is a small chance that some of these CNAs and some of those chlorines interact with each other. And the only way we get an actual 2 is if the sodium only interacts with water and the chlorine only interacts with water. So this interaction throws it off some. So the largest an I can be is simply the number of ions present. So even if it's something crazy, Na2SO4, NAs are each an ion, sulfate's an ion, this has a potential I of 3. We call it an ideal I. The potential or ideal I is just simply the number of ions there. The actual amount of the I, or the actual value we'll see, is going to be slightly lower than that, just because the interaction between the positive and negative ions will offset it some. Now, in perspective, we got some actual values, and we can see how they affect. So small charge species, so sodium and chlorine, both of them positive, H and Cl, both positive, and the actual Van Hoff I is very close to the number of ions. So we move the charges up. That positive 2 is just so darn attractive to those negatives, they start interacting too much, and this drops from the ideal, which is what these are going for. Now, we're not actually going to use we're not going to try to calculate the true value like from this chart. We're going to be given the Van Hoff factor or solving for it based on our information. But it just changes our equations ever so slightly. So if we see here, all these equations are exactly the same as we saw before. They just have that little I in front of them. And you're just going to get this I from that Van Hoff factor, or an ideal I, so the number of ions, and actually calculate the same type of thing we saw. All right. Last thing we actually talk about in this chapter is colloids. We're not going to need to do any math with these. So colloid is a solution. It's mostly homogeneous. But these don't necessarily affect the colloidal properties the same way. And I say don't necessarily. We get some interesting features here. What I mean by that, think milk, which is actually little proteins dissolved in water. That is very difficult to get that pure water out. If it was easy to get out, powdered milk would taste excellent, because the only thing you'd have to do is add water back to it and it suddenly tastes like milk. But if you've ever actually had that milk from powder, you know it doesn't quite taste the same. And that's simply because the process of removing the water damages some of those proteins. But a colloid is really a suspension. It's particles floating around in there. They're just doing it nice and evenly, so it looks homogeneous throughout. Even that mud, like they're showing here, it'll stay that way. As long as that stays moist, it's going to look like that a while. Now, if it's muddy water, if you actually stop the motion, you would see the dirt particles settle. But this is like a sauce almost, that powder in there. And even the fish tank, if you think about, if you ever seen it when there's little particles floating around in there, like the, I don't know, you can see it floating around throughout. So colloids are suspensions. They just don't settle out. Now, various colloids can happen. The only one that's really not on here is gas and gas, because it turns out gases always mix. They never form colloids. But any of our other phases mixed with each other can actually form colloids, even solids. Solid mixed with solids can be alloys for metals. They can also be suspensions. Opal, for instance, is actually an actual individual separation of suspensions. Paint is solid dissolved in a liquid. And as that water dries, you're left with the solid behind. But these are all types of colloids, and just familiarize yourself with the names of them and some examples. All right, last little thing, talking about, since we're talking about intermolecular forces, this is just a neat thing that comes up right now. Soaps versus detergents. What do we use them for? Technically, they are used for the same purpose, cleaning things. But we use detergents in totally different places than soaps, and there are some weird advantages. All right, turns out detergents have zero problems with hard water. Soaps, though, if you mix them with hard water is just water that has high amounts of calcium or magnesium ions in there, which isn't that big of a deal for the water. Matter of fact, if you were to drink water with calcium, magnesium, it still tastes like water. You can hardly tell that. But when soap gets in contact with calcium or magnesium, it makes an insoluble compound. Soap scum. So this soap scum that builds up on the wall, it is a very hard rock-like substance because it's a huge molecule, and about the only way to get rid of it is to actually physically scrape it off. So a little bit of elbow grease type thing. You will never see that in your clothes washer as long as you're using detergent, and even your washing machine for like a dishwasher, because detergents don't actually do the same thing. Detergents do not actually care what the positive ion is. They stay soluble. This one down here is not really used too much because that one actually survived a little bit too long through most of our water treatment facilities, and the wastewater coming off, or the now clean water coming off wastewater treatment facilities, would still have too much soap. So we don't use this particular one too much anymore because it's got too long of a life. It still pops up, it's just not the go-to one per se. Alright, so if these don't actually form soap scum, how come we don't actually use them to wash ourselves? Technically, it's because they're too good of cleaners. You and me and anybody that's made out of mammals, our bodies produce a little bit of oils that are necessary to keep the skin nice and healthy. Detergents can wash all that away, and actually has a detrimental effect to your skin. A little Most people find it to be an irritant to use detergent, and it really is because it's pulling all the good oil out of your hand. It dries up your skin. Hate to imagine what it do to your hair, but not necessarily a good soap, and that's the distinction. Just intermolecular forces and how they react. All right, that gets us done with this chapter. Very long chapter. If you made it through in one go on YouTube, go you. I would imagine most of your fellow students viewed this at most about 15 minutes at a time. Have a good day.